Hi friends, this is Dr. Anar Patil. Today we will see Coriolis component of acceleration. So let's start. Friends, what is Coriolis component of acceleration? So you know this mechanism. It is a quick return mechanism wherein what you see this A B is a crank which rotates with some angular velocity omega. Now there is one more link OD. This is OD, which is pivoted at point O, isn't it? It means what? This link OD oscillates like this, and on this link OD we have slider B. This slider B slides on the link OD like this. So if you see carefully what happens, this point C, also called as coincident point, which moves along link OD, simultaneously it also rotates, isn't it, about one more pivot point A. Now in this case we need to consider one more additional component, and it is called as a Coriolis component of acceleration. So this point C, I just told you, is having simultaneous motion, isn't it? It rotates and slides. So the tangential component of acceleration, F, so this is a tangential component of acceleration, FCR. CR is Coriolis component of acceleration of the slider B with respect to coincident point C on the link is known as Coriolis component of acceleration. And friends, this is always perpendicular to the link OD. Remember this. So this is a Coriolis component of acceleration which is always perpendicular to this link OD. Now, the magnitude of this Coriolis component is calculated by this formula 2 omega v, where omega is angular velocity of link AB. So this is link AB, it's omega, you know, and v is velocity of slider B with respect to coincident point C. Now, how to find this velocity? So you have to take it from velocity diagram. So remember this. Now, by knowing these two omega and v, you can find Coriolis component of acceleration 2 omega v. Okay, so let's move further. Now, friends, OA is fixed link. If you refer this figure, OA is fixed link. So you can see this is O, this is A, fixed link. Then AB is a rotating crank. The direction of rotation is given like this. And OD, this link O and D is oscillating link. It oscillates about point O. Yes. Now you have to remember. So there are 2 points. If you consider slider B, and there is one more point C. So this C is a coincident point C on a link OD. Okay. And which is sliding on link OD and rotating along with link AB. So in the last slide we have seen it. Now this is very important. Acceleration of slider B with respect to coincident point C will have 2 component of acceleration. Number 1 is Coriolis component of B with respect to C. So this is also we have seen in the last slide. How to draw it is very important. Draw perpendicular to link OD. So remember this. You have to draw this perpendicular to link OD. So this is Coriolis component of acceleration. So there is one more centripetal component of acceleration. Up till now we used to draw centripetal component of acceleration first, and then we used to draw tangential. But remember, whenever there is a slider sliding on a link and rotating with a crank, we'll have Coriolis component of acceleration. And first of all, you have to mark or draw FCR, which is tangential component, FT. So FCR is also we call tangential component, and which is perpendicular to the link. And second component is centripetal component of acceleration. That is, you have to draw a parallel to the link OD. So friends, remember this. The first component is FCR. The second component is FC. CR means what? Coriolis component. And FC is what? Centripetal component of acceleration. So this is a C. Okay. So make correction. Now, once you draw these two components, you need to remember there are two more components. Which are those? Acceleration of point C. This is point C, isn't it? Coincident point C with respect to O. We'll have two components of acceleration. Number one is here, now it is FC, centripetal, and FT, tangential. Okay. So with this information, friends, we can attempt one simple example. Let's move. Now before that, the direction of Coriolis component is very important, and to find the direction you have to consider two things. One, how the link is rotating, what is the direction of angular velocity omega, and what is the direction of this velocity v. These two will decide this direction to omega v. Now remember, this is the direction of the link, okay, and the slider is moving in upward direction. So when this is the case, the direction of Coriolis component is or will be in the direction of rotation. So this is the direction of rotation, isn't it? Now if you see, if the direction of rotation of crank is clockwise like this, then and the slider is moving in upward direction, friends, the direction of Coriolis component will be towards or in the direction of angular velocity. Now it is very interesting in third case. The velocity component is moving in downward direction. The direction of that vector is vertically downwards, and the direction of rotation of the crank is anti-clockwise. In this case, remember this, the direction of Coriolis component will be opposite to the direction of rotation of this link, because the slider is moving towards the center of rotation. Okay. Similarly, this is center of rotation. Crank is having angular velocity omega in clockwise direction, and the slider is moving in downward direction. So the direction of Coriolis component will be opposite to the direction of rotation. So with this information, we can start to draw a simple example. So friends, this is a given example. You can pause it and read it, and remember you have to find the angular velocity, and that I have calculated here. Now you have to first draw a space diagram. So this is a space diagram. You know how to draw. You have to take scale, isn't it? 1 centimeter is 100 mm. So with this scale you can draw the space diagram, and as you know, omega AB you have calculated in the last slide, it is 12.57. You can find velocity of B. So this is B, that is slider. Velocity of slider with respect to A is omega A BA into length of that crack. So it comes 1.9. Okay. Once you calculate the velocity of B with respect to A, we can draw velocity diagram. And to draw this velocity diagram, again you have to take some scale. Okay, 1 centimeter is equals to 0.5 meter per second. Okay, let us draw with this scale. So here are the steps I have written to draw the velocity diagram. So everyone know the velocity of slider B with respect to A will have a velocity BA perpendicular to this link AB. So first of all, locate a fixed point OA, then draw this vector. So this is V B A to get this point. So you have 1.9 velocity of BA is 1.9 meter per second. We have seen in the last slide. Okay, so as per the scale, 1.9 divided by a scale 0.5, you will get some centimeter. So you take this centimeter from O to this point, you will get this point B. So this is VBA. Now the next vector will be as the slider slides along this link. So draw a line parallel to the link OD. I have drawn it. Okay. Once you draw this, so step one is over, step 2 is over. Now friends, this is very important. Now velocity of coincident point B dash with respect to this OC, you have to mark. Step number 3 is very important. Okay, so let's draw that vector which is perpendicular to this link. Okay, so this is velocity of B dash. Very good, very important. Velocity of point with respect to the link or point, you may say O. So this is B dash O. So this is B dash O. Okay. Now it will intersect somewhere here, and this is friends B dash. Now once you get this is B and this is B dash. Now you have to find point C, and by ratio of distance you can find this point C. So use ratio of distance to find C, and how you can find it? O B dash upon OC small OB dash upon small OC, isn't it? So you know OB dash, you want OC, so you can find OC and locate this point C. Once you get this point C, next velocity of D, so you mark by, we have completed point 4 number point. Next step is velocity of D with respect to C is perpendicular to this link. So this is velocity of D with respect to C, isn't it? So I have drawn perpendicular to this CD, and finally the slider slides. So draw horizontal line passing through this OA. So friends, you get this point D. Okay, this is velocity diagram. I hope everyone can draw this. Okay, so once you draw the velocity diagram, our next step is to draw acceleration diagram, and wherein we need to remember